Hi, everybody. So I got my calculator working with fresh batteries. Oh, we already had that open, so cannot be approximated accurately. All right, so we're comparing the sun's mass to the Earth's. So if we take, let's see, it depends on how we want to compare it. Let's say Earth divided by sun, 5.98, 5.98 times 10 to the 24th. Divided by 1.99 times 10 to the 30th. And that gives us, how many zeros is that? 1, 2, 3, 4, 5, 3. Okay, so we have 1, 2, 3, 4, 5, 3. So that is the result of that. So if we take out 2 zeros, that would be 0.0003%. So that is the, and I know my penmanship sucks on this thing. I'll get better at it. But that is the percent of Earth's mass compared to the sun. It is 100,000th, 10,000th, 300,000th of the sun's mass. Pretty crazy ratio there. Uh-oh. There we go. Clear drawing. All right, so how about the relative mass of the Earth to a mosquito? All right, so this time we'll do Earth divided by mosquito to see how many times bigger the Earth is to a mosquito. So we will take 5.98 times 10 to the 24th, and we will divide that by the mass of a mosquito, which is 10 to the negative 5. So this is going to be a huge number. So that gives us 5.98 times 10 to the 29th power. So that is, I don't know, that's like, that is 6 with 29 zeros behind it. A ridiculous ratio to compare those two. But I mean, you're thinking about the tiny little mosquito compared to Earth. So if we had to write that out, we would have 598000000, and that would go on for a really long time. I guess we would have 27 zeros because 2 of those are a 9 and an 8. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. That many times bigger than a mosquito, which is a useless statistic, but now you have it. Now, clear that. What fraction of the universe's mass does our galaxy contain? Now, that's at least interesting. So let's take 10 to the 42nd power divided by 10 to the 52nd power, which is just 1, or that would be 10 to the negative 10th. That's how that works, right? Yeah. Yeah, so you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, I was right. So you've got 1 over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is the ratio of our galaxy to the rest of the universe. So it is 10 zeros. So that's 1/10,000,000th. So our entire galaxy, everything that you see in the night sky, all of those stars, all the planets, all the exoplanets around all of those stars, all the comets, all of the black holes, the supermassive black hole in the middle of our galaxy, all of that combined is 1/10,000,000th of the size of the entire universe. So small you could kind of ignore that. All right, 4. So this warning, this small feelings incoming. What fraction of the galaxy's mass does one human make up? So this is basically your mass compared with the rest of the galaxy, not the rest of the universe, just the rest of the galaxy. So a human, they have it estimated at 10 squared divided by 10 to the 42nd power. Yikes. I don't know if you guys can see that. Let's see if this will show up. That is the answer. A ridiculously big, or I guess a ridiculously small number. So if we take let's see, what's the rule on that? You take the top one, subtract the bottom, or no, bottom one, subtract the top one. I mean, I guess that's how we could do it. You got to find the difference. So that would be 40 zeros on the bottom, right? I don't want to count that. But I believe that is 10 with 40 zeros, 1 with 40 zeros. So if we want to look at your mass compared with everything else in the galaxy, you would have 40 zeros. So you would have, no, I don't want to write that out. That's just obnoxious. 1 over 10 to the 40th power. So a human's mass is absolutely insignificant to the entire galaxy, and I have a couple of videos I show my astronomy kids to show the relative size of massive stars and huge black holes and galaxies and things like that. But then it zooms back down on the size of a human, and it makes some people feel super uncomfortable because it gives you that small feeling. Here are some approximate values of length and time. If you want to look over this, you can pause it. This has really large distances, such as the distance from the Earth to the most remote known quasar, which is very far away. Right here, we have the distance from Earth to the nearest galaxy, Andromeda. Then down here, you have all the way down to the diameter of atomic nuclei and protons. Then you've got approximate time intervals, really long time, like age of the universe, age of the Earth, down to the time interval for a light to cross a proton, which is just ridiculous. Why? I mean, light's the fastest thing, and a proton's the tiniest thing that we've got measured here. So that's just a ridiculously small time interval. It'd basically be instantaneous at 10 to the negative 24th seconds. But if you want to look at more at that, go ahead and pause this video. Those images are pretty decent resolution, so you should be able to read them. Next, communicating your measurements. This is extremely important because it really doesn't matter what your measurements are if you can't communicate them to other scientists. That's kind of the whole point of doing science, is communicating with the rest of the world, or at least with the rest of your field, what your findings are, because that's why we do science, right? So number one, should you use scientific notation or metric prefixes? So for example, we have 0.85 times 10 to the negative 15th meter, which is really, really small, or 0.85 femtometers. So one is scientific notation, one uses a metric prefix, and I've got the metric prefixes down there for you to use to look at. Now, it depends on what you're trying to communicate, right? On whether or not you should use scientific notation or metric prefixes. For example, if you are looking at maybe the error in a length measurement, let's say the meter bar, right? The platinum iridium bar of a meter had changed. We don't want to put that in femtometers because that doesn't really tell us how much a meter changed, right? Then you'd have to know that a femtometer is 10 to the negative 15th. So if I were communicating that, I would say that a meter, that bar, changed by that many meters, because we're using the same unit all the way through. When you start jumping units, it's kind of hard to understand what the information is trying to be communicated, right? Now, if you're talking on a much smaller scale, you might want to use femtometers. For example, if we're talking nuclear sizes, you would want to use 0.85 femtometers. You wouldn't want to use 10 to the negative 15th meters, because all of the things you're talking about would be on such a small scale. For example, 0.85 femtometers, that's the diameter of a proton. That's the diameter of a proton. So If you're talking about nuclei and neutrons and protons, you're already talking on such a small scale that you don't need to use such an obnoxious scientific notation. You can use the common vernacular that everything's being measured in something like a femtometer or possibly a picometer. But it really depends on the information you're trying to communicate. So you need to keep that in mind. Number two, if something increases 4 orders of magnitude, how much did it increase? Now, an order of magnitude has to do with exponents, right? So order of magnitude, if you increase by 4 orders of magnitude, you increased by 10 to the 4th. So you would basically multiply your number by 10,000. Am I dumb? Is that 10,000? Yeah, that's 10,000. Okay. Yeah, so you would multiply your number by 10,000. That's what happens if you increase by 4 orders of magnitude. Now, if you increase by 4-fold, that's very different. That means that you multiplied by 4. Now, it's very different multiplying something, say, let's say you're investing, right? That's a big topic lately, especially with apps like Robinhood. Oh, excuse me. Let's say your investment is growing, right? And it grows 4-fold. That is a huge jump in money, right? To increase by 4-fold, that means that you increase by 400%. That's an incredible jump. Now, if your accountant or say someone is your investment broker comes to you and says, well, this quarter you increased by 4 orders of magnitude on your investments. If they mean that it multiplied by 4, but they tell you 4 orders of magnitude, that's very different because you either multiplied by 4 or you multiplied by 10,000. So you need to make sure that when you're using these kind of terms, orders of magnitude, fold, things like that, or using scientific notation or metric prefixes, make sure that you're using them appropriately because you might just be confusing the audience, confusing whoever you're trying to communicate to, because the communication of your information is critical. That's kind of like I said earlier, that's the point. We don't, I mean, sometimes we do science for fun, but you do science so that you can find the answer to something and help somebody with a problem or solve a problem to reach a solution, things like that. But if your information is not communicated appropriately and properly, then it's going to be misunderstood, and misunderstood science is a big issue. Just ask the vaccine community. Now, this is one of our last slides for this one, I believe. Now, last thing I want to leave you guys off on. Let's talk a little bit about problem solvers. A problem solver is someone who can visualize or draw the situation, identify the goal, collect your givens, conduct necessary research, and plan the multi-step path. These are the things that problem solvers are going to need to be able to do within physics. Now, depending on your problem, maybe you only need to do 1 or 2 of those things. Maybe you need to do all 4, and then you maybe need to do some more. But someone who can solve a problem is able to do these 4 things in some kind of way or another. Now, you might have to try more than one path, or you might get to use more than one path, and those are going to be 2 different mentalities as we get further into this class. Sometimes you have to solve for one thing before you can even try to solve for the solution. So there may be more than one path that you have to take. And to do this, to gain these skills, you need to experience as many problems as you can with practice. Now, I will be giving you guys homework and take-home tests and the unit tests, all to hopefully prepare you for the AP exam. And it's all treated as experience. You need to try all of the problems and do your very best so that you can figure out all of these different ways to approach a physics problem. And now, how can all of this be achieved? All of this is done in this class through homework, and mostly because, and I say that on homework because homework is really completion grade. You either did it, you tried it, or you didn't, and you've either got you got full credit, half credit, or no credit. Because homework is essential for growing problem solvers. Um, if you want to be successful in this kind of science, not just in it for a career or anything, but just with this kind of mentality or this method of solving problems, homework is going to be essential. And the reason I put this in is because I want to emphasize how important taking the time to actually try and get through all of the problems for homework is. Because you can do absolutely no homework and just ace everything in the class and possibly get a high B, low A. But I don't recommend that because you're not getting all the practice that you need. The homework sometimes takes a special spin on some of these problems that the take-home test and the test may not have. So I recommend you. Of course, I mean, I'm the teacher. I'm going to tell you to do all your homework, but don't do it just because it's an assignment. Do it with the mentality that you need to try and figure out what is the method to solve this problem. Because those methods, if you focus and pay attention, they will repeat all throughout physics. Some of these methods you've used with ASCII. Some of these are new methods that you've never used before. But all of this experience and trying as many problems as you can is what's going to make you a good problem solver. That is all we have for this video. This was over measurements. So, and I'll piece these videos together because I ran out of batteries midway. But if you guys have any questions, ask your questions in the discussion board, and we can discuss it as a class. And if we get in person, then we will be able to discuss it in person as well.